Good morning. Welcome to Stats class online. We're doing hypothesis testing, which is an accumulation of all the stuff we've already done, put together, starting to see the puzzle pieces form a beautiful mathematical picture. For the remainder of the semester, whether on campus or not, you will see these same 6 steps over and over and over. Most of them you've already seen before. Hypotheses. Those were a 7th grade science type of thing. You may not know specifically what these two are, but hypotheses are educated guesses. Critical values, those are your tables, whether Z if you know sigma or T table when you don't know sigma. Alpha is the percentage in each tail. It's also known as the percentage you're willing to be wrong. N is your sample size. DF is the degree of freedom, which is known from its N-1 formula. The next formulas are called sampling distributions, Z and T. Calculated values come from them. And then finally, we draw on the big bell curve of life. We would draw in our mean at 0 standard deviations from the mean, 3 sigma limits in each direction, and move on from there. So let's think more specifically about the null, the HO hypothesis, and the alternative, known as HA, or it could also be called H1. In short, the null means nothing, but more specific, as in nothing new or nothing has changed. Nothing has changed from what someone has already told you. It's listed as HO. Someone told you this, so it's the currently accepted value. Mathematically speaking, it is. And when something is, we usually say it's equal. However, HO could be a regular equal, a greater than equal, or a less than equal. And for clarification, HO, the null hypothesis, is usually what they say, whoever they is. For instance, a magazine blurb or a USA Today graphic. So just a few brief hints. HO is what they say. Some article, some graphic. HO always has an equal sign. Always. HA is us. In other words, the researcher. We can make a claim as well. Find out that these two will always be mathematical opposites. This means if they say equals, we say not equals. If we say less than, they say greater than, but because they always have the equals, theirs would be greater than equal to. If they say less than equal to, we say greater than. Always mathematical opposites between HO and HA. HO always has the equal sign. For instance, if I give you this situation, they say, this is the they say the mean dollar amount lost by victims of burglary is $2,222. That's what they are saying. That is the claim. Using that claim, they say that the mean, the mu, equals 2,222. That's what the HO or null says. U represent the HA, the alternative hypothesis. It will always be the mathematical opposite of HO. If HO says equals, the mathematical opposite for HA says not equals, using the same number. Push pause to test yourself to see if you can find the claim. Then check your answer. The mean number of times that adolescents engaged in vandalism during the last 12 months was 3.5 times, is the correct answer. This translates to, they say, the HO says that the population mean, the information we don't know but we're proposing or hypothesizing, the population was 3.5. Mathematical opposite should say not equal to 3.5. But wait, there's this wording that says less than. We believe less than. We would say less than 3.5. Since HO and HA have to be mathematical opposites, if we hypothesize less than, they get to keep the equal sign. HO always has an equal sign, and we change theirs to the mathematical opposite of less than, which is greater than. They become greater than or equal to. Moving to step 2. The critical values. These are your charts. If you know sigma, you're going to go to the Z. If you don't know sigma, you're going to go to the T distribution. A few hints here. We are almost always going to use the T-table because sigma is usually unknown. So also let me remind you that if your degree of freedom is not on the chart, use the closest number below. For instance, not on the chart, go to the closest number below and you would read the DF equals 45. Other hints. If the wording of the problem says different, this means it's a two-tailed test. You would read the two-tailed value of your chart because your picture would say it could go this way to the tail or it could go this way to the tail. So you must put in plus or minus on your T value. If the problem says greater, that implies you're going to the right, which means you have a one-tailed value, and your picture would show go this way. If the wording of the problem says less than, this implies go to the left, also going only in one direction. So it's a one-tailed test. Your picture would look like this. Go to the left. You must put in the negative sign. It doesn't show up on the T-table on its own. So back to our National Insurance Association question. There's nothing in the problem that says sigma. In other words, sigma remains unknown, which means we should use the T-table. If we're using the T-table, we need an alpha. If we are 90% confident, then we are 10% unconfident. Just like the T-table shows us, alpha and confidence are going to be complementary to one another. N is 25, which means we have 25 minus 1 or 24 degrees of freedom. I see the word different. Different means two-tailed. So using my t-table, my critical value using alpha two-tailed at 10% right here, which would be the same as 90% confidence right here. It's the same column reading down. 24 degrees of freedom. See where they intersect. And I have a t value that would be positive and negative because it's two-tailed, of 1.711. My picture would show 1.711 right there, and negative 1.711. Again, I ask you to push pause and try it for yourself. Picking out the pertinent information, I see that alpha is 0.05, N is 20 adolescents, which means our degree of freedom is 19, and I see the wording less than. Less than is going to imply that I only have one tail. Looking at my chart, one tail at 0.05, 19 degrees of freedom. The value that I see is 1.729, but because the problem said less than, I must put in the negative sign. Step 3, we're going to calculate using the sampling distribution formula. You've seen it before. Listing out the pertinent information, we say, is 2022? Hint, mu is usually in the first sentence. So mu is 2,222. Keep reading. We see conducted with 25 victims. That indicates N. N is 25. Keep reading. The mean loss for those 25 people, so it's an X bar, a sample mean, is 2,150. Keep reading. Standard deviation for those same 25 people is 700. Now plug in your formula and do your calculations. Since this is a t-score, we get 3 decimals. So if I round this 2, it rounds the 4 to stay where it is, rounding down, giving me a calculated value of negative 0.514. Again, push pause and you try, then check your answers. Mu is in the first sentence, it's 3.5. 20 adolescents, that's N. Number of times they vandalized the property, meaning these 20, is 3.1. So X bar, the sample mean, is 3.1. S, the standard deviation for those 20 people, is 0.9. Plug the formula in, and you get negative 1.988 rounded to 3 decimals. And now, step 4, drawing the critical from our chart value and our calculated value from our formula. Here's the recap of what we've done so far. When we draw We start off with the critical values of positive and negative 1.711. Call that T naught for our critical value, 1.711, and our negative 1.711. We're going to color in from that line to the tail on both sections. Color to the closest tail. These are called rejection regions. Now when I draw in my calculated value of negative 0.514, so negative 0.5 standard deviations below the mean, it would be right in here. Again, push pause and you try. Negative 1.729 for my critical or chart value would fall here. Color into the closest tail. Then draw in your calculated value of 1.988. So a couple of hints. If your calculated value falls in the rejection region, reject. Reject who? Reject them. If the calculated value does not fall in the rejection region, fail to reject. This is another word for accept, at least for now. Accept who? Accept what they have said. You cannot prove your information yet. Since our calculated value does not fall in the rejection region, we will fail to reject. Fail to reject the null. The null has been accepted. It's correct. Our hypothesis is not. Pause the video and see if you can decide the correct answer. The calculated value falls in the rejection region, so we will reject. Reject who? Reject the null. The null can be rejected. It is incorrect, which means our hypothesis is correct. Now for our last step. We interpret the conclusion. What does it all mean? 3 parts, always included. Number 1, what % are you willing to be wrong? That's our alpha. Step 2, is there enough information? Information of what? Information to say what we think was happening. For instance, let's look at the next problem. Here's our recap. My statement for the interpretation would say, at the 10% significance level, there is not enough information to show the population mean is different from 2,222. Again, pause and see if you can come up with the correct interpretation. At the 5% significance level, there is enough information to show the population mean is less than 3.5. So stop for a moment and think about the 6 steps, since we'll be using them for the rest of the semester. The null is HO. It's what they say, and it always has the equal sign. Alternative is what we think, and it's mathematical opposite to them. Step 2, the critical values from the chart. Step 3, the formula. Step 4, where you draw Step 5, if your calculated value falls in the rejection region, you reject the null. We are correct. Also in step 5, if you draw and your calculated value is not in the rejection region, you fail to reject the null. They are right and we are wrong. And finally, the interpretation. At the what percent significance level, is there enough information, and what is it you, the HA, are trying to say? So you should be able to answer these questions. HO always has an equal sign. How do you know which sign goes in HA? It's from the wording of the problem. It's also the mathematical opposite of HOs. The critical value when sigma is unknown comes from the t-table. Why do we use the sampling distribution? That's from before, where we have an n that is larger than 1 because we're measuring things in groups. If you reject the null, the calculated value falls in the rejection region. Which hypothesis is considered right if you fail to reject the null? The null is considered correct, so the hypothesis considered correct would be HO. And finally, your homework. Please, please, please do this assignment. It will make the rest of the semester tons easier. Good luck.